Okay. Hello, good afternoon, everyone. How's everyone doing? Can you all hear and see me? Use the reactions, please. Okay, thanks. Okay, so today we will go straight into the tutorial. I think last time we lost a fair bit of time just talking through the materials and already, of course, there are detailed lecture videos available and so on. So I'm not really planning to spend that much time on the notes in this session, unless anyone would like to ask any questions there. So please let me know if you'd like to revise anything in those lecture notes. Otherwise, I plan in this section in this session to just go into some problems and to start solving some of those sort of seminal problems that we have in this course. So I'm planning to work through the tutorial 2. So in the Dropbox folder, I uploaded a number of days ago several tutorial questions. So there are some questions from tutorial 1, which I hope you've worked through. And then in this one, we'll be working more on tutorial 2. So tutorial 2 is more about the energy balance. And so you've had the 2 lectures on the energy balance, the details of, in the first set, we were looking at just developing the energy balance and taking care not to double account for reaction heat or things like that. And then in the second set, we were looking at navigating the equilibrium plane and looking at that. If you have an equilibrium reaction, if you have a significant reversibility in your reaction, then you might be limited in terms of how high your conversion can go. And then we were looking at applying cooling and so on to navigate the plane so that you could still achieve a high conversion. So in a sense, we'll do one of each of those types of problems. So in the first one, we'll look at the energy balance, the basics, and just being able to determine what the relationship between conversion and temperature would be. And in the second instance, we would look at negotiating the plane. So again, as more people have joined, we'll be going more into tutorial type questions now, unless anybody would like to ask anything about the theoretical work that's covered in the notes and the videos. Okay, so I tend not to watch the hands going up so carefully. So please go ahead and unmute yourself and then ask a question if you'd like to ask anything. Okay, so I'm just going to share screen here. And it's this tutorial 2 we're looking at now. And so in question 1, we have a CSTR and we are given the molar flows. So this is the reaction that we have. So 1 molecule of A reacts with 2 of B to give us 2 of C and 2 of D. And we are given the molar flow rates of A and B entering that CSTR. And we are also given the inlet temperature. So we are given the stream. We are also given the thermal properties. So we are given the heats of formation of all 4 components. And we are given the heat capacities of all 4 components as well. And the first one, simply, what's your standard heat of reaction? And then what's delta Cp for the reaction? And so that's basically working out some numbers there. And then we want to know, is the reaction endothermic or exothermic? And you can probably already tell, it looks like your products have a higher energy. Well, we should really work it out, but it looks like the products have a higher energy. So that means on balance, energy will be taken from the surroundings to maintain the, to form those products. Energy will have to be taken in from the surroundings. So that starts to look like an endothermic reaction. And then, so should one apply heating or cooling to get a better outcome? So if it's endothermic, that means taking energy in. That means if we add heat to the system, we get a better outcome. So we apply heating, probably, and then we want to design a CSTR to give us 80% conversion. And we are given some specifics about the heat transfer around that CSTR. So we looked before at a jacket. So in the lecture videos, you'll see we discuss a jacket around around the CSTR in some detail. But the same framework applies even if it's a heating coil or cooling coil, right? That's the beauty of heat transfer. It doesn't matter what exact geometry you've used. It doesn't matter whether you've arranged your heat transfer fluid as a jacket or as a coil through the reactor. You can represent all of them as UA delta T. So all the values are given there for that CSTR. We are also reminded what the energy balance looks like for the CSTR. So this one is very much a matter of just putting together the numbers, and I guess it's a kind of warm-up problem for energy style problems. Okay, any questions or comments there so far? Okay, so heat of reaction. What's the standard heat of reaction? And let's just do it from scratch, right? So question 1, we know that the standard heat of reaction delta HR equals, and we can say delta heat of formation plus delta CP, and then T minus T ref. So that's the usual thing. And our delta heat of formation, we know is given as the sum of those stoichiometric ratios. So you can say sum of I, and it's mu sub I over mu sub A, what? Mu sub A, and that's heat of formation of component I. Oops. So this is heat of formation of component I, and then that's products minus reactants. So yeah, and of course I'm missing a minus sign here. Right, so you can just rewrite this then as so your new A over new A. So you can write this for each of your species in the reaction. So of course, new A over new A is simply going to be a 1. So let's check this out. So we can say this is 1 or minus times 1 times, I'm just going to reuse that. So 1 times the heat of formation of A, so super F sub A, and then plus new B over new A. So you can see new B is minus 2, new A is minus 1, so that's a plus 2 times the heat of formation of B, and then plus, and then new C is plus 2 and new A is minus 2. So that's going to be a minus 1 H super F sub C. And then for D, it's, well, it's the same thing. So it's going to be minus 1 times H D. Right. And all these heats of formation are given in the problem. So these are simply specified here. So you stick the numbers in and you work this out, and it looks like on balance, as we said, your products, sorry, I'm not sure. I think I may have been looking at the wrong line here. I can see the heat capacities have higher values here. You've got that 750. But in terms of the heat of formation, clearly the reactants are going to be higher. So with your reactants being 700, so it's 2 times 700 and 1 times 300, and then minus 200 and minus 175. Certainly, your reactants are going to have a larger contribution here. So the number is going to be more negative, right? So this is going to be minus of a larger positive number. So this is going to be a negative. And so you will have on balance an exothermic reaction, right? And just to be a bit careful there, your reactants have a higher heat. So your heat of formation, if you like, the chemical potential energy of your reactants are higher than that of the products. That means for the reaction to proceed and form products, you have to give off energy to the surroundings. And so heat will on balance accumulate as thermal energy in the surroundings. And so we observe that as an exothermic reaction. Any questions or comments there so far? So it's a similar process for delta CP. So I'm not going to actually do it. You can see it's just more of the same here. So you can work out the delta, well, the standard reaction heat and the delta CP, and then you just substitute those as numbers in, and then that's basically the dependence of your heat of reaction on temperature. Let's see something in the chat. So are the coefficients for the heats of formation for C and D not supposed to be -2? So let's see. Thanks. You're correct. I don't know why I thought that was a 2, but it's yeah, it's +2 divided by -1, so that's 2 and 2. Thanks for that. So that was up to be 2 and 2. Okay. Yeah. So there's that. Let's see. Any else? Okay. Great. Okay. And let's keep going here. So that's how we work out the standard heat of reaction and the delta CP. You'll recall there's also that other little trick. If you have reversible reaction and you have E1 and E2, you can also estimate the heat of reaction that way. We'll see that in the next example. Okay, so those two parts, that's how we do that. And let's move on now to the third one. So we've said it's an exothermic reaction, and so we know actually we need to apply cooling. And by the way, here I'm a little bit neglecting that I should actually go ahead and work out this contribution, right? So I've said clearly from the heat of formation that the reaction heat is negative, but of course that's only this part. We should also add in this part. And so please go ahead and do that. In a way, I'm just assuming that that's going to be the overriding factor. I'm not actually sure that I've given the right numbers to do that, because most of the time in reality, this term is quite small in comparison with this. And quite often the numbers here are around hundreds of thousands, right? 200,000, 300,000, that's typically what you see here. And then this contribution is on the order of thousands. So normally if this one is negative, we just think of it as an exothermic reaction. But don't just assume that. It might be that the numbers that I supplied here are not compatible with that or something. Well, so this is times 10 to the 3, and then these are in the hundreds. So that's consistent with that. This term is going to be much smaller than this one. So if this one is negative, then very likely this is negative as well. But of course, you'll check that with the numbers. Okay, so now we want a CSTR that gives us 80% conversion at steady state for that same problem. And then we are given specifics about the heating here. So let's just copy this energy balance here. And let's just separate that a bit. Okay, so we want to solve for the exiting temperature. So we are told that the CSTR will exhibit an 80% conversion. And then we do have a heating fluid at 400 Kelvin. And what's the temperature leaving the reactor? And I'm just going to sketch here a bit. Okay. Where are my colors? Okay, so here's our CSTR. Excuse the shaky hand, it's not as nice as a chalkboard, right? Yeah. Okay, so here's your heating side of things. So you've got some heating fluid entering and leaving here. And we are told it's coming in at 400 Kelvin. And we don't exactly know what it will leave at. Yeah, that's supposed to be a question mark. Okay. And then it's a CSTR, so we do have flow through here. Come on, colors. Yeah. So it's a CSTR, so we've got flow through here. Right, so the reaction is going on here, and across the walls of this reactor, we are getting heating of the content, heating or cooling. It's all relative, right? It depends what temperature, and the temperature might be 500 here. So even though this one is 300, let's try this. So if your sure, this brush is too slow. So if your temperature here is 300, so you're feeding at 300, and you've got a heat transfer medium at 400 here, it might well be the case if your reaction is exothermic enough, your temperature here might well be much more than 400. It could be 600 in here, in which case this 400 is actually playing the role of a cooling medium. So it all depends what we are trying to do. If there's some temperature we are trying to stay close to, so that's actually what decides what we use here. So whatever it is, let's keep going with the numbers. We have an estimate for the heat of reaction. Maybe let's unpack this term next. So we need beta CPI. So it's some beta capital beta C sub pi t minus t in. So that's going to be, and in this problem, we are told that we have, where is it? So we have 10 moles per second of A and 40 moles per second of B. And remember when we defined this inlet flow ratio, that was simply beta I equals F sub I over F sub A. So it's not a mole fraction, right? This is by no means a mole fraction. You can see it's just a ratio of one of the molar flow rates to the molar flow rate of component A. It's an arbitrary choice for A to be a basis component. So don't expect this to be a number between 0 and 1 or anything like that. Okay, so for component A, of course, that's just going to be a 1. So that's 1. Do we still have time? No. 1 times. So 1 times, and then CPA. And here CP of A is 200 plus, and then CPB is going to be 40 moles divided by 10 moles. So 10 moles, 40 moles per second divided by 10 moles per second times CPV. And CPB is 300. So times 300. Okay, so that times T minus T in. T minus T in. So the T in here is, what was it, 300, right? Yeah, this feed stream is at 300 Kelvin. So that's 300 Kelvin. Right, so that's that term taken care of. And then we are given quite a lot of information about this side of it. And, it's straightforward plugging in numbers, but I'm doing this in detail because you have to make sure you're getting the right numbers in. Don't get confused. This T in refers to the reacting fluid. So that's T in is the reacting fluid. TA is the heat transfer medium. So that's the 400. So so that's one term taken care of. And then let's write the other one. So Q equals UA TA minus T. So we are simply told U is 600 watts per meter squared per Kelvin. So you can see the area influence there quite easily. So that's 600 times, I should say times like that. And then the area, the heat transfer area, 3 meters squared. 3 and then TA minus T. So TA is 400 minus T, which is your reactor temperature. So this temperature difference is driving the heat transfer. And it looks like here we have gone and made the assumption that the flow is high enough, right? If you look back at that energy balance development, we are assuming here that the flow is high enough that you have the same temperature throughout this jacket. So imagine a jacket, it's like an annular space outside of your reactor. So if you have a flow, if you have a slow flow through, then there's enough time for heat transfer. And let's say this was highly exothermic. So then probably your temperature here will rise, right? The temperature in the reactor will be so high that you'll start heating up this heat transfer medium, and the heat transfer medium will leave at a higher temperature. But if you use a very high flow rate through the jacket, then the space-time on the jacket side is low, right? So I know we introduced space-time for the reactor in the sense of a reactor, but you can easily define space-time for anything that's flowing through any space. So you can say, oh, this heat transfer fluid is spending on average 2 minutes here, or it's spending 2 seconds here, whatever space-time you design it to be. So if you have a low enough space-time, in other words, if you have a high enough velocity here, then you can assume the 400 is the same right through that jacket. And in the notes, we looked at how to test that assumption and so on. In this development, looks like we are just assuming it to be true. Okay, so that's why we've got just 400 minus, TA minus T. For the temperature on the reactor side, assuming that T is the same everywhere, that's more a consequence of perfect mixing, right? So that has nothing to do with space-time. We are assuming one temperature in this reactor, and that's just because everything is so perfectly mixed, right? A CSTR, we assume infinitely fast mixing. So we've got the same temperature at all points in the reactor, including on the walls. And so that's why we treat it as just one temperature T. But it's an unknown temperature T, right? So we know we are feeding at 300 Kelvin, but we don't know how much time the fluid is spent. Well, but we don't know to what extent the reaction is happening as yet. We haven't talked about it as yet. It's a function of the reaction itself. So we don't know how much the reaction is happening here. So we can't say anything about the temperature inside the reactor as yet. right? We've only so far unpacked a bit about the influences from the heat transfer medium and so on. Okay, so that's that term, that's that term, that's there. And we are told that the conversion is 80%. So we are simply given x equals 0.8. Okay. And in fact, that's it. You now have this term is only a function of temperature T, the reactor temperature. So that Q term, the only unknown there is T. And then in this term, which we wrote here, you can see the only variable is T. And then the heat of reaction, the whole of parts A and B were about finding this as a function of temperature T. So the whole thing here is a function of T, and you are given X. So it's quite straightforward. You can solve this for T, right? So I'm not going to plug the numbers in. Please go ahead and do that. And let's see that we get sensible values for T there. Any questions or comments on that? And I'm just trying to see, is there anything in, that's basically it. It's as easy as that, right? So this first question, it's very easy. Okay, so let's move on to question 2. Okay, let's see, there's a question. So what is TA? So TA, this is TA. That's the TA is the temperature in the jacket. So TA. I'm actually a bit better with the mouse than the pen. So TA is the temperature in the jacket. It's the temperature of the heat transfer medium. Generally speaking, we should be defining TA in and TA out, but we are saying if the flow through here is high enough, then we can treat this all as one temperature TA. Okay, and let's see, there was another one. For delta CP is a minus sign. Yes, that's right. So the other question was here, sorry, here, where is it? Here. So yes, there's a minus sign for the delta CP as well. So the we can write here delta CP formation C sub P. So this is CPI. C sub P. C sub PI. Yeah, so that one also has the minus sign. Okay. So does the 400 Kelvin stream act as a cooling medium? And we actually don't know as yet because I didn't work it out. So when you do the calculation, you'll find out whether it's above or below 400 Kelvin. So whether or not this thing is playing the role of heating or cooling is totally dependent on the temperature that you have here. So if this is at a temperature of 600, then the 400 is actually cooling it. If this thing is below a temperature of 400, if it's 200 or something, then heat is being transferred in the other direction. So so what's nice is that energy balance makes no attempt to say that heat flow is in any particular direction. So when you write a balance like this, right, it's all just written according to a certain convention. So it's like a reaction rate. When we write RA by itself, that's just assumed to be the rate of formation of component A. And then the fact that RA might turn out to be negative, that's just because the numbers worked out like that. So all these things are defined in a certain way. So so TA and T, those are just the temperatures in the heating medium and in the reactor respectively. And the fact that the heat actually travels from here to there or there to here, that's just a function of how the numbers work out. So so in a way, you don't have to figure it out. It's not like the equation is going to change. It's just that the transfer will be in one direction depending on what the numbers are. Does that answer the question? Okay, thanks. All right, let's look now at yeah, question 2. So in question 2 now, we have a reversible reaction. So you have component A being converted to B and B is being converted back to A. And you are given all the kinetics. So you are given the kinetic rate constant for the forward reaction and for the reverse reaction. So just to write it a bit differently, where are you, pen? Come on. Okay. So A and B. So the forward and the reverse reactions. And so here you have the forward constant, and here you have the reverse constant. Reverse constant. Right, so so we have this as a very explicit function in temperature. So this is nice. We just have to stick in the temperature, and we'll know the value for K. And now we are told we want to do this in, well, we are told up here, we want to run this in a CSTR in series with a PFR with some cooling between the two. So a CSTR now in front of a PFR. What's a nice? So a CS. Whoa. So you've got a CSTR in series with a PFR. And there's interstage cooling. So you've got a cooler here. And you've got your PFR here. So it's not standard notation, by the way, but I draw my PFRs like that. I use a little double line here to remind myself. You've got little plugs flowing around here. This is standard notation, although very badly drawn here, but that's supposed to be a CSTR. And then my kind of secret notation here, when I draw heat exchangers, if it's cooling, then the heating medium's temperature go up. So I use that arrow to remind myself, oh, that temperature is going up, so this must be a cooler. So anyway, that's just a quick drawing. And so we've got these two reactors, CSTR and PFR. And I guess we want the volumes and the exit temperatures and things like that. So let's see here. So, and in fact, we define it more at a high level here. So in contrast to the first problem where everything was specified, now it's more like a design problem. And we are saying, well, we just want a nice high reaction rate. So it says here, we want the first reactor, the CSTR, as high a reaction rate that we can get while still getting a reasonable conversion. So that's a nice kind of designy way of saying things, right? It's not like, oh, for this temperature with that, it's more like try and get a nice high rate but still give me a good conversion. That's a typical kind of engineering design sort of a thing. So that's for the CSTR, and then for the PFR, we are saying we want reasonable length. So and it says such that the reaction stays 10 K short of equilibrium. And we know if we get too close to equilibrium, then your rate is so low that you can't, for very small increases in conversion, you have to add massive amounts of volumes. So, so you want to stay inside of 10 Kelvin, 10 Kelvin away from equilibrium, and you are accepting that as being your criterion for the PFR. And as I say, this is kind of a high-level way of giving a design spec, but if you follow the lectures, and as we'll show just now, this is actually enough to precisely design these reactors. Okay, then more specifications are given here. We are given the heat capacity of A, and you might think that's not enough information, but we'll see it actually is. We are also given the temperature, so the feed stream, the temperature is given, and the flow rate is given, and yeah, well, the units of rate, okay. The interstage cooler returns the temperature back to 300 Kelvin. And by the way, you know, these paragraphs of text can be a little hard to keep track of. So it's always a good thing to try and write on your, to put the information on your diagram. So it says it's coming back to 300 Kelvin. So this cooler does a good enough job that we come back to 300 Kelvin here. We know we were fed at 300 Kelvin here. So something's going to happen in here. It's going to heat up or cool down, and then we'll get a different temperature here. And then this, well, we know it will be higher. This is a cooler. We'll come back to 300 Kelvin, and then we'll come out at some temperature here. And we know this is something like 10 K shy of equilibrium. Right, so always work with a little sketch. It's going to be much easier to keep track of everything. Okay, so first question, draw the maximum rate path and 10K to equilibrium lines. And I should have gone a bit further to say we are provided with this graph, which shows us iso rate lines. So fortunately, the proportions are a bit wonky. Let's just and move over Zoom. Okay, so here you can see for 0.01, right, a nice high reaction rate. I know it's less than 1, but in SI units, this is actually quite a high reaction rate. So you've got a high reaction rate here, and then you've got a lower one, and then a lower one still, and lower and lower. So you can see we are slowly converging up to this line here. So this is the equilibrium line. You've got a high rate here, a lower rate, lower, lower, lower. So the more you approach equilibrium, the lower your reaction rate is going to be. So you think of this whole thing here, in fact, the whole plane, you think of this as just a plane or a field of reaction rates. And so your reaction rate, we know, is going to be a function of temperature and concentration. And a proxy for concentration for us is conversion. So when given a particular conversion, and implicitly your entry concentrations. So when given a conversion, you can identify all the concentrations in the reactor. So we know the reaction rate, it only depends on concentration and temperature. And so this on this plane, it's a plane of reaction rates. And we have some lines on that plane, so that helps us figure out approximately what the reaction rate is if we pick any point there. We aren't drawing lines up here, although we could do. So as hopefully you've seen in the lecture video, you could draw lines up here, but those would be lines for the reverse reaction where B is going back to A, which is not something we want to do. We don't want product being converted back to reactant. So that region is useless from our perspective. That nature, it's just everything happens. So we want to design to stay in here. And of course, we want nice high conversions. So we'd like to see coming out of our, coming out of the train of reactors here, we want to see some nice high conversion because then it reduces our separation costs. So if you have a low conversion, that means you'll have a high amount of reactant still, then you'll have to do more separation. You'll need bigger distillation columns and so on before you can get a nice high purity product. So we would like to get a nice high conversion coming out here. But we know the problem with doing that is that as you go up in conversion, you can see you are getting closer and closer to that equilibrium line. You are getting to the low rate region. And I guess we've said it many times now on this course, but as you accept higher conversions, that means your concentration of reactant is going down, and that's why your reaction rate is going down. And now this plane is explicitly showing us that relationship between reaction rate and conversion. So you can say nice and generally, oh yeah, when conversion goes up, my concentration, so you can say all that. But this plane now shows you precisely how much it's going down by. So this isorate plane is really a useful thing for doing our design. Okay, so anyway, we want first to draw the maximum rate line. And that takes some, it's not such a straightforward thing. If we want to say we want a maximum rate, then you could say to me, well, then just go down into the corner here and stay there, right? So clearly, if that's the low rate and that's low, and then it's getting higher and higher, and then clearly the maximum possible rate is down here. But that's not what we mean when we say maximum rate line. By maximum rate line, we are saying we know that we have a reactor and things are going to happen there, and conversion is going to change and temperature is going to change. So as all that is happening, where would we like that to happen? So we know, for example, if you start on 300 Kelvin, your temperature is going to rise or fall. So you're going to move in temperature. And then as the reaction proceeds, of course, your conversion is going up. So your conversion is rising. And well, we know this is an exothermic reaction. So here your temperature will rise as well. So your conversion and your temperature are going to increase in some way. And we would like to know how far should that line go? Where should we stop? Where when we move along that line, we are basically considering different size CSTRs. Maybe to explain that a bit, let's just take the design equation. This one. So this is our CSTR. So if you think about what this equation is saying, if we use larger volumes, we will in effect be getting higher conversions. And it makes sense because if you let's say you've got a fixed flow rate here, and then you start increasing the size of that space, then on average, you'll be spending more time in that reactor. So it's more time reacting. And so it makes sense to us that we should have a higher conversion. As we increase the volume, we'll get more conversion. So when we talk about this plane, and we talk about moving around on the plane, when we say the conversion is rising, we are basically making that happen by considering larger and larger volumes. Excuse me. So, okay, let's just plot a line, and then we can talk about that a bit more. So let's take the energy balance. Where's a nice energy balance? Okay, can't find one, so let's just write here. Okay, yeah. Let's just write our energy balance here as X equals, so it's, and I'm writing the adiabatic version of this, so minus some beta I, so pi minus T in. So all that divided by delta HR. Right, so that's the adiabatic equation. So this is a general thing that's true, that as you increase in temperature, your conversion will rise. So, and this applies to any reaction. In our case, delta HR is a negative number. It's exothermic. And in fact, I'm not sure we did say that. If we just look here, so remember we said that delta HR could be estimated as delta HR is approximately E1 minus E2. So here, if you look at E1, 28,000 and E2, almost 40,000. So E1 minus E2 is going to be a negative number. So delta HR is negative, and yeah, as a number, it's negative. And so that will cancel with that minus sign. And so this is going to be positive, right? If you look here, all this is, and let's say we consider values of T above T in. So if T minus T in is positive, then obviously these ratios are positive numbers, and heat capacity is obviously positive. So all this is going to give us a positive number. So let's draw that now. Okay, so unfortunately, the quality of the image is quite low, but you can follow the construction anyway. So we are told that we start at about 300 Kelvin. And let's see, can I draw this well? So, okay. So we start at 300 Kelvin, and we know we are going to move up in a positive direction like that. So we need the slope of the line now. So for the slope, it's as simple, if it's a slope, right, on a xt plane, then t is basically the variable. So I'm just wanting to move that outside of the ratio here. Right, so this is basically our, this is the gradient. So we just need to calculate this as a gradient. And I see, where did, that was from the previous one, right? So let's work it out now for this problem. So we now have minus, and then it's some theta I CPI. So we are feeding, well, component A, right, theta A is always 1. So this is going to be 1 times CPA, and then plus, and then theta B is 0, right? We are told that it's pure A in the reactor to begin with. So where is that? The fresh stream contains just component A. Right, so it's a very texty way to write it, but if it just contains component B, component A, then component B, theta B equals 0, right? There's no inlet flow of component B. So we can see that it's this thing in the numerator is just that CPA. And CPA is what? Heat capacity 28.82, right? So 28.82, that's the heat capacity of A. And then we want to divide by the heat of reaction. So the heat of reaction, we said, is 28,000 minus, yeah, 28,000 minus 39526. 39526. Yeah, we don't really need that one there. And then we can work this out. And let's take out our big machine gun to work out that simple thing. Let's use Python to calculate this little, so minus 28.82 divided by 28,000 minus 39526. And I'm actually going to multiply that by 100, so 100 times that. So it's the answer is 0.25. So it's 0.25 divided by 100, right? That's how we can write that. And the reason I'm writing it with that 100 is because it helps me to plot this. I've forgotten the t minus t in part here. So now if I want to plot this line, I can see number one, when t equals t in, x equals 0. So t in was 300. So we've got 300 here when x equals 0. And then we've got a gradient of 0.25 per 100. So that's the gradient. And we can read this as x is 0.25 when t increases by 100. So this is 200. Here's 300. So we can say that's a point here. So in other words, let's see now, drawing a line is not so easy in Photoshop, to be honest. What is that? There's the pen tool, right? Okay, so let's see now. Just to move it is such an issue. Okay, anyway, we've got this line. So we've got this line now, which is which has the gradient that we want, and we need it here, not at from 300. So we know at 400 it's going to be 0.25. We can also say at 500 it's going to be 0.5. So at 500 it's 0.5, which is here. So we've got this line. Okay, so that's the operating line for that CSTR. So we start at 300 Kelvin, and as we increase the volume of that CSTR, we will be moving through points, moving up like so. And then in this region, we get very low rates. So for a tiny change in conversion, right? If you consider a very small change in conversion along this line, a very small change of conversion here might be hundreds of cubic meters, right? The closer you get here, right, it goes to infinity here. So you want to know where to stop along this line. And now a way to do that is, and of course you can do this nicely with your graphical construction, but I'm just going to draw some lines here. Well, let's think about this line first, right? Let's consider moving along this line. So we know as we increase the volume of the CSTR, we are moving closer and closer here. And if you look at what's happening down here, think about the rate that we have at this point. So here, clearly, our reaction rate is a value somewhere between the value on this line and a value on this line, right? This point is lying between this blue line and this red line, right? So the value of the reaction rate here is somewhere between these two numbers, 0.001 and 0.0001. And then as we move along this line, we are moving closer and closer to the blue, this teal colored line. So your rate actually went up as you moved along here. So you got to a nice high rate, 0.001. And in fact, it keeps going up. So it keeps going up because now we are moving closer to this purplish line. So you are getting closer to 0.01. So the rate is going up. And then you're getting to a point here now. So as you moved here, you are actually moving closer to the purple line. So your rate is going up. But you get to a point somewhere here where you start moving again closer to the teal line. So as you move along here, and it's a bit hard to imagine because you're not moving directly away from the purple line, you're actually moving almost parallel to it, but definitely somewhere around here, you are again moving back closer to the teal line. So you are going to another lower rate region here. So from here, you were nicely increasing in reaction rate was going up. Then you get to a point where the reaction rate starts going down again, and then it really starts going down very fast here. So, so there exists some maximum rate here. There's some point here where you are nice and close to this higher rate region. And that it would be a nice place to stop, right? We would like to operate that CSTR at that nice high rate region. We know that there are higher conversions available, but in terms of our spec, right, when we declared our design strategy, if you like, the criterion was that we want a nice high rate for our CSTR. And that is a good choice because we know CSTR has issues with reaction rate. So we want a nice high rate for the CSTR. But it's kind of hard to see where to stop along this line because, the way it's drawn, partly. But we could say, well, what if we, this line is a little bit inconvenient. What if we were closer to this line? So let's say instead we were here. So let's say we were instead here. So I'm saying, what if our starting temperature was here and that was the operating line? Then we can say clearly, this is the maximum rate, okay? And then equivalently, what if we had started here? Then we could say, well, then here is the maximum rate, right? If I move to the left, I'm going closer to the red line. So those are lower rate regions. If I move to the right, I'm going to lower rate regions again. I'm going to the red line again. So that's the best point. And you see, then all we need to do is keep doing that. So for each of the available ISO rate lines, we can draw a line parallel, right? Because we know we've got that same gradient everywhere. So we can draw a line parallel and get a nice gradient going. So we can say here, look, there's a point here, and then here's another point here. So I know those are nice high rate regions. So let's say the other point was here, and then the other point was there, and so on. So now we've got a series of points, and we know if our line happened to be there, then that would be the best point for us. So now let's go and connect the dots. Let's just connect these together. And again, you can draw this much better than me. And now we have a so-called high rate line, okay? And so if we go back and look at our 300 Kelvin starting point line, we can say, oh, then the intersection with that line must be where I will get my high rate region, right? So that's how we can cleverly estimate the region where we've got the high rate line, the high rate point. And we can say, well, if I operate on this point, then that's going to be the best possible reaction rate I can accomplish. So starting at a temperature of 300 Kelvin, that's the best choice for me. If I go any further, I'm going to get lower reaction rates and hence bigger reactor volumes. I will have higher conversions, but my conversion is more expensive in that region. I need more reactor volume to get the same delta X, if you like, right? Compared with a delta X here. A delta X here is very expensive. Okay, so that's what I can do for conversion. And then you see this clever idea that, well, we know it's not going to be nice if you go further here. So, and it looks like the maximum conversion then we can ever get is only about 0.35. And so the clever thing is we say, well, why don't we just cool ourselves back to where the rates are friendlier? So we just go back to 300 Kelvin, right? And that's the interstage cooler. Where did we draw that? Over here? No, not here. Okay, anyway, we cool back to 300 Kelvin. And then the PFR takes over. Right, maybe I should pause there. Any questions or comments so far? Okay. Okay, so now we've managed to operate our CSTR at a nice high reaction rate. But for the PFR, we realize it's not the same situation. Right, with the CSTR, we have one reactor space and it's perfectly mixed. That means the reaction rate is everywhere the same in that CSTR. For the PFR, we acknowledge it's going to be moving on the same line. What's another different color? Okay. So for the PFR now, we are going to be moving along this line. And remember that adiabat that we derived was not specific to CSTR or PFR. The adiabat, by adiabat, I'm meaning I'm meaning this thing. So this adiabatic equation, that didn't come from any specific reactor. We derived that independent of reactor type. So the same equation applies to the PFR. So the second part of the question has a plug flow reactor, and that plug flow reactor is also adiabatic. So I know we have interstage cooling, but on the reactor itself, we are not adding or removing heat there. So the same equation applies for the PFR as well. And I think we have a question. So the question here was, are all these red lines parallel? Yes, so all these lines are parallel. And that's because if you look at your adiabat, we had calculated the gradient here. This was 0.25 divided by 100. And then you have T minus T in. So when we draw a new red line, it just means that we are considering a hypothetical alternate inlet temperature. So we are just talking about different T ins. So in this case, T in was 300. So for this red line, in this red line, T in was close to 250. For this red line, it's T in was 200. So these are exactly the same concept. These are all adiabatic lines. These are all operating lines in the CSTR. Your reacting fluid, if you start at 200, it's going to react up along that line. So whatever your inlet temperature, it's all going to increase with that gradient. Does that answer the question? Okay, thanks. Okay, so we've gone from the CSTR. We know that's a nice high rate region. That was our criterion. Then we cooled back to 300 Kelvin. And then we are now considering a PFR. So again, we know the PFR, it's adiabatically operated, and so we'll be moving along. And yeah, this line is intended to be parallel to the red line because it's the same gradient, it's the same adiabat. But now the criterion is different. So let's read that part more carefully. We'd like to design the PFR to be of reasonable length such that the reaction stays 10 K short of the equilibrium temperature. So first off, what's the equilibrium temperature? So let's go back to this 300 K starting line. So, as you increase the volume of that reactor and you get closer here, you'll need larger and larger reactors, and at infinity you get closer and closer here as you tend to infinity. So that is the equilibrium. That defines the equilibrium point, and we can use that point to work out the equilibrium temperature. So if you look down here, that temperature is about 437, let's say, right? So the temperature here is 437. So that means if you start at 300, you will, the best you can do is go to a temperature of 437 Kelvin. So 437, if you like, is a kind of constraint. It's also, if you like, a point to avoid, right? It's a point where you have this terrible reaction rate. So the kind of rule of thumb for us is we want to stay 10 Kelvin short of that point. And so here you can see this point. And so if we pick a point just 10K short of it, let's use a different color. What haven't we? Okay, this one. So that's the equilibrium temperature. And then these are increments. Let's just call these dashed lines increments of 10. They're not quite, but let's just say, right? So we take 10K short of that line. So that's where we are saying we would stop. So if this had, so we know it's a CSTR, this line is supposed to be a CSTR, but if it had been a PFR, then we would say, okay, equilibrium is there, so 10K short of equilibrium is here. And so we can do that again. So here you can see the equilibrium temperature, and then 10K short of that is somewhere here. And then here, 10K short might be somewhere there, and so on. So 10K short might be there. So in the same way that we drew the locus of points for the maximum rate line, we can do the same thing for the 10K line. And okay, let me try and use the pen. Yeah, I have to reboot the pen now. It's okay. So it's here. Okay, so we can produce the locus of points for 10K short of equilibrium as well, right? And we can see here, so our PFR is starting here, and and so as we progress up this line, then that's the right place to stop. Notice also, this is quite different to what we had with the CSTR, right? With the CSTR, we go boom from here, we go on there, right? The CSTR, it's from the inlet, the inlet operation. This is totally inlet, right? It's 300 Kelvin, zero conversion. And then you enter the CSTR and it's instantaneously mixed, and it's a different temperature and a different conversion, right? So it's like a boom from here to there. That's what you see in the CSTR. It's different here in the PFR. You are entering at 300 Kelvin and conversion of around 0.25. But as you move up this line, you will find all those points in your PFR, right? So if you look 1 centimeter into your PFR, you will find a point here with that conversion, and so on. So you will be able to observe all these points in that PFR. And in a way, this introduces a new consideration. So you see, with the CSTR, it was kind of straightforward. We just wanted the whole CSTR to operate at that nice reaction rate. With the PFR, if we chose to stop here, right? Remember, with the CSTR, we went and stopped on that so this maximum rate line. Let's just draw that again. So remember, this is our maximum rate line. Right, so with the CSTR, we knew the whole CSTR was sitting on that maximum point. With the PFR, however, if we choose to go and stop here, then that means only at the end point of that PFR. Let's draw it here. So your PFR, and if we were plotting reaction rate across that PFR, then you would see something like this. Your rate here would be going up. So So your rate would be going up, and so if you chose to stop at that endpoint, what you'd be doing is getting to, so it's almost like saying, just when it gets good, it's over, right? You'd be positioning your best possible reaction rate right at the end. So you don't want your best reaction rate right at the end. You want to move that to be the average operation in your PFR. You'd rather have a situation like this instead. You'd want your maximum rate to be somewhere in the middle of your PFR. You want the average operation of your PFR to be at a nice high rate. And that's in effect what we've done here. We've crossed over the maximum rate region, and we've gone as far as the 10K to equilibrium line. In practice, 10K short of equilibrium works fairly well. So this is a good choice. So the suggested choices in the question were not random. Those are actually the best choices you can make if you have a CSTR in series with the PFR. So in the CSTR case, you set your whole reactor on the maximum rate, or if you like, if you consider all the fluid in the CSTR, if you take packets in that fluid, every single packet will be sitting and happily carrying on at that nice high rate. In your PFR, you've got differences, you've got zones where the rate is lower and so on. But the way we've chosen it, we've chosen to step over the maximum. So at least on average, it's a nice high rate in between. So those are good criteria. That is a good choice for the design of these two reactors. Okay, any questions or comments there? Right, so from that construction, number one, we now have the exit temperature from this reactor. Where did we draw that thing? So we gone. Okay, so we have the temperature now that's coming out. So let's draw it again here. So we had the CSTR here, and we said we had the cooling, and we have the PFR. And we know we are coming back at 300 Kelvin here. We have 300 Kelvin here. And now we know that we are leaving here at, it's about, it's about 400, let's just call it 400. So it looks like about 400 here. And the conversion here is about 0.25. So X is 0.25. And so, of course, we use the same 0.25 here, only this is at 300 Kelvin now. And then for the PFR, we can also look here and see the temperature coming out here is about 360. So this is 360. And the conversion here is about 0.45. 0.445. Okay, let's see the question. So the question here is, would it be better if we reversed the order of the CSTR and PFR and kept the criteria as they are? And my first response is, go ahead and try it out, right? You see, in terms of these numbers, in terms of conversion and temperature, right? The numbers we are just writing down here, it actually makes no difference, right? Oops. In terms of these numbers, there will be no change. If you are saying you are going to stop on the maximum rate point for the PFR, or the CSTR, you would draw exactly the same line. Same thing here. If you're saying, then we cool back to 300 and then we straddle the maximum rate line and stop at 10K shy of equilibrium, you will draw exactly the same line, right? So in terms of what you draw here, you would then just draw different symbols in these two positions. So it would look like the same from that perspective. However, the next step is to estimate the volumes of those two. And you see the volumes are going to be different. Remember, you estimate the volume of the CSTR as the product of X and 1 over R, and you estimate the volume of the PFR as the integral of 1 over R in dx. So it's actually better to have the CSTR first because you take advantage of the higher rate and you get, if you try and do the CSTR second, you'll end up with a larger overall volume. And as I say, please go ahead and do show that. So in terms of your actual accomplishment of, a final 0.45 and those temperatures, you'll see no difference. But in terms of the volumes, VCSTR and VPFR, you will likely get a higher volume if you switch those around. Does that answer the question? Okay. Okay, thank you. So let's start with that, right? Let's talk about estimating the volume in each case. And it's actually quite straightforward now that we've drawn these lines. So for the CSTR, I think if I just write slower, it works better. VCSTR. We just use the design equation. So if you, well, just, okay, never mind. So we know for the CSTR, FA naught X equals RAV. So VCSTR is FA naught X over RA. And FA naught, I think, was given as 5 moles per second in the question. And then your X, you just go ahead and say, well, I know I'm stopping here. I know my X here is 0.25, so 0.25. And then divided by RA. So you look at this point. So here it gets a bit tricky. You have to kind of imagine a logarithmically varying thing. So I would say this is about 0.008. So RA is 0.008. Right. So I worked that out by just saying this point is between these two colors, so the purple and the teal, and so it's a number more than 0.001. And then if you imagine logarithmically scaling, you'll get a high, well, it's a high density here, and then for like a double jump there, it will be a change of 0.001. So I'm estimating that this 0.008 sitting here between 0.001 and 0.01. So that's the rate there. So and that's all, right? That it's as easy as that. That's how you estimate the volume of the CSTR. For the PFR, there's a bit more to it. For the PFR is VPFR is FA naught integral of well, I'm going to say dx and RA like that. And so we can, so that's strictly true, but we will approximate this. We can say this is approximately the same as FA naught A naught, come on, times the sum, and then we'll write here delta xi over ri, adding up over the i's. So we should really discretize this path. What's another? So here we discretize this path. Okay, I don't want to do so many. So between here and here and here and here, right? So if you let's take this panel to begin with. So in this region, number one, we have to estimate the rate. So so here we're going to say this equals FA naught, which is 5. FA naught, you really have to imagine what I'm writing here. Okay, so here delta x in this region, it's about 0.1, right? It looks like 0.35 minus 0.25. So let's call that 0.1, 0, 1 divided by, and then the rate over there. You can see this region is sort of in between the teal and the red. So between the teal and the red, so I'm going to call that 8 times 10 to the minus 4. So 8 times 10 to the minus 4 plus, and then you do that for the other parts, right? So here it also looks like about 0.1, 0.1, and then the rate here, yeah, it's probably a bit closer to this line. So it's a slightly higher value. So let's just call it 9 times 10 to the minus 4 plus, and then the other one looks a bit smaller. So this delta x is more like 0.08. Well, more like 0.05 or something. But anyway, the rate here is closer to the red line. So that's going to be low, yeah, lower now. So maybe this one is about, let's call that 4 times 10 to the minus 4. So of course, when you answer these questions, there's no way I can expect you to be very precise, and it's more like you have to be choosing the right kinds of estimates rather than expecting to get accuracy to the nth order. So that's how you can estimate the integral for the plug flow reactor. And by the way, just look at how easy these things are to do, right? When you look at the equations, it looks, with all the summations and the thetas, and it looks complicated. But when you unpack just resolving into components and taking little discretization increments, these are all easy things to do. You can do all this like a back of the envelope type calculation. Right, so that's how you estimate the volume of those two. And so please do try that exercise, reverse the two and recalculate those volumes and see if you get higher volumes overall. Okay. And I think we would probably stop there. Just want to see if there's anything else. Oh yeah, here there's a nice question. So we can see that you can navigate this plane by cooling down, right? So you can think of it as a strategy to get to higher conversions and so reduce your separations. You can look at cooling down. Can you think of other strategies, right? Because remember, you've got now these two units and you can do whatever you want to them. You as the design person, as the creative bright spark on the team, it's up to you to say, look, I think let's try and engineer this, or let's look at that energy balance. What are all the terms, right? That's one approach you can take to looking for ideas. you can say, let's look at the balance. Is there something clever we can come up with? So if you go and look at this balance, you can say, well, I know I need to navigate that plane, and I've got this unfortunate line, this equilibrium line sloping in the wrong place, and I want to find my way up around it, right? So if I look at the equation, there are things we can do here, right? So we've so far we've fooled around a bit with this inlet temperature. We can't really do anything about the heat of reaction. That's nature's constraint. That's what we are trying to navigate. But here we can think about something, right? Our inlet flow ratios. Um, and you would say, well, what are you talking about? Do you want to go and add product now to this? And that's not going to help. Well, we don't know. It might help us navigate a bit better. But the other side of it is we can add whatever we want into that reactor. It doesn't just have to be reactant or product. So we can see there's a factor here. And if you think about it, right, if you're starting down here, what if we could make this gradient? Why are we stuck to this kind of shallow gradient? Why can't we just push the line straight up like that, right? So we can, in fact, do that quite easily if we add a high heat capacity inert to the system. In other words, if you just add another term here, so let's say there's some component C, which has a nice high heat capacity. So you've got a CPC, which is a large value in comparison with CPA and CPB. So you use a nice high capacity inert, and you can add as much as you like. It's an inert, so it's not going to affect you negatively. Well, except if you're worried about dilution, but let's say it's gas phase and it's not going to, just the pressure will go up, then you have safety problems. But anyway, so you can change the gradient of that line by adding an inert here. And so you can actually get away with progressing along the line like so. So that's one of the strategies. There are other strategies as well. There's so-called cold shot quenching. So in cold shot quenching, you are saying, well, let's go back to these shallow lines, right? So you can say, look, I've got a reactant at 300 Kelvin. The moment I put it in the reactor, it's going to force my reaction. My reaction is going to force me to higher temperatures. Instead of loading the whole reactor with the whole stream, let's say I bleed off part of that stream and I send it around the reactor to rejoin. So instead of using interstage cooling, you actually it's like the reverse of recycle. You are jumping over the unit and entering the next unit. So you're feeding the same cold reactant in at one of the future units. So if you do that, then you will be reducing the temperature and also the conversion. You'll be adding reactant to a product. So you'll be pushing your conversion down, but you'll be getting to a high rate region. And you would do that if you have an easy to separate mix, especially if you have, let's say, the reactants in the gas phase and the product in the liquid phase, or the reverse. So it's easy to separate them. Then if separation cost is not a concern for you, you can think about just bleeding reactant to join future units. Anyway, we'll talk about that cold shot possibility more later. So for now, high capacity inert, that's part of this question. So think about that, and and then do questions D and E. Okay, so that's pretty much all I wanted to cover today. Any questions or comments there? And please note the test. I did send you the provisional dates. It does look like those dates are going to stand. So next week, actually, you have a test coming up, right? So the test will cover everything up till and including today's material. There is a bit more on the energy balance. So there'll be another video during the week that I'll send out, but that won't be covered in the test. So everything up to and including this navigation of the ISO rate line plane, that would be covered in the test. Okay. So if there are no further questions or comments, we'll leave it there for today. See you next time. There we go. So to confirm, there is no energy balancing. There's always energy balancing, but you mean in the test? So I'm saying, yes, there is energy balancing in the test. So up till and including today's work, that's all about energy balancing. It's just that there is another subsection on nonlinear dynamics. So nonlinear dynamics is not in the, so everything up to and including today's work, which is about energy balancing, that's in the test. Okay. So as they say on YouTube, like and subscribe. It will make no difference to me. My videos are never going to get to the point where that helps. Yeah. Okay, how long will the test be? I'll have to confirm that one. It's listed for 3 hours, right? I don't know that. I'll make the 3 hours available. I think. Okay, let me confirm that one, right? I'll set the test first and then confirm how long it is. But it will be under the 3 hours, of course. Okay. All right, that's it for today then. See you next time.